Hi all, we're going to do a little tutorial on voltage dividers. So either if you've watched the video of me demonstrating various aspects of voltage dividers or I showed it to you in class. So I want to get to the heart of this so you can work on problem sets. Keep in mind that voltage dividers is just an application of series circuits. Okay, so we've learned about series circuits that there seem to be two distinct disadvantages of that. If you remove one resistor, none of the others will work, right? You'll get no current flow through them at all. And then if you have full connections, as you add more and more resistors in series, it reduces the power output of each, which kind of defeats the purpose of putting them in there. But there is one important advantage. And to get an idea of that important advantage, let's look at a possible scenario. Okay, so let's say I have a lamp board, a bulb that goes for those lamp boards that's rated for 3 watts of power. There's my P. And I can't have more than 6 volts of potential across it. Okay, in other words, it's designed to get 3 watts of power when it's plugged into a 6-volt source. However, I don't have a 6-volt source. I have a 9-volt source. How can I light that bulb with a 9-volt source without blowing it out? Well, I can do it by putting that bulb in series with another resistor. Okay, in other words, we use the series circuit as a voltage divider. I want to take that 9 volts from my source and divide it into 2 pieces. One for the resistor, that's waste, but I'll live with it, and then leaving 6 volts for my light bulb so that it can work properly. So how do we find the value necessary the resistance though? Okay, I want to figure out then what specific resistance would I have to do. Well, we can do a number of things with this. So I say we can use what we learned from terminal voltage lessons. Well, we might not have seen that yet, depending on which cohort you're in. So let me show you one approach. This is not the only approach. If I know the power that the bulb is supposed to get for the voltage, then I can figure out how much current it should draw when it's working correctly. So I can use the relationship that P equals IV, where I know I'm going to get 3 watts of power when I connect it to a 6-volt source. Okay, that's how it works ideally. So the current in there has to be a ½ an amp. All right, so what I'm going to have here, if I haven't made this clear, I'm going to have this EMF. That's my 9 volts. I'm going to have across that 9 volts of potential is R1 and my bulb. I know that I want the bulb to be 6 volts. So we can also use the KLR, the loop rule that says the drop across here plus the drop across here has to add up to 9. So if I want a 6-volt drop here, then that means I want a 3-volt drop across there. And if I know that I get ½ an amp in the circuit, because that's what the bulb is going to work best at, then I have that piece of information. So I can say the R of the resistor, I'll just put R of little r, is going to be equal to the voltage that I want across divided by the current. Well, I want 3 volts, which I figured out from KLR. I know it has to draw ½ an amp, so that tells me that the R that I want to put in there is 6 ohms. Okay, so by placing and making this 6 ohms, I can figure out the resistance of this bulb based on knowing that the voltage is 6 volts and ½ an amp, right? That 6 divided by ½ is 12 ohms. So let's see if it all checks out. 6 plus 12 gives me an effective resistance of 18. And if I have 9 volts across it, 9 volts divided by 18 gives me ½ an amp, which is what I want. So there's a lot of different ways you could approach this. All right, so let's move on now. We've already used a variable resistor as a voltage divider in lab. Okay, I showed you that. How I can take a resistor, and the symbol for a variable resistor, if this is a resistor, a variable one has an arrow across it, meaning you can change that. Okay, so that's one way we can change resistance to change voltage across it in a divider. Other ways that you should be aware of are voltage dividers used in sensors. Okay, one sensor that I showed you in class was a light sensor, and that's called a light dependent resistor. Oops. or LDR for short. And here is the symbol. This is an IB symbol, so they'll be in your IB reference tables for that. So there's your resistor. There's kind of like a light thing around it, or a circle around it, and then the light comes in through these arrows. All right. And the idea behind a light-dependent resistor, and this is something you'll have to remember, is an incident light increases, the resistance to LDR decreases. So what does that mean? So let's say I draw a symbol. Let's say here is I'm going to use this symbol here, and I'm going to connect to it a generic resistor R. Okay? So if I shine light on the LDR, this resistance goes down. So what happens to the voltage drop across it? Well, if the voltage drop by Ohm's law is I times R has gone down, then the voltage drop is going to have to gone down. So when you shine light on it, the voltage drop across here goes down. Therefore, the voltage drop across the resistor, it could be the LED that I showed you, goes up, and it lights up. Okay? And you can set up circuits where the circuit would turn something off rather than turn something on. But the point is, you can change the voltage across your device by using a sensor that changes the voltage across it through some environmental change, which affects its resistance. Okay, other ones that we want you to be aware of are something called a thermistor. Okay, thermistor is kind of a blend of two words, thermal and resistor. It's a sensor in which resistance changes with temperature. That's where the therm comes from. And there's a symbol for a thermistor right here. Okay, and it's very useful in digital thermometers. That's how they work. You have something in there that's resistance changes with temperature. You calibrate that resistance to a voltage, and that voltage change then can be used to output an actual temperature. Strain gauge is another one where the output voltage depends on tiny extensions or compression. So like when we do a strain gauge or a force sensor, you pull or push on something, you stretch or compress a material whose resistance changing, who therefore changes the voltage across it if it's a part of a series circuit or a more complex circuit. And then you can get different outputs, which is pretty cool. Okay, so let's do an example. All right, we're going to use an LDR. So I have a circuit shown here with an LDR in it. All right, so here's my LDR. I have a 12-volt source, and I have an 800-ohm resistor. And what I'm interested in is the voltage output across here. In other words, I can make a new circuit here so that when it drops across here, something happens. Doesn't matter what that happens, but what we want you to understand is that V out is what we're interested in. Okay, so what we want to understand is that if there's no light on the LDR, okay, the resistance to LDR is 2 mega ohms. So it's a very, very high resistance. And so if I've got 2 mega ohms across here, it's not shown in the schematic. The schematic is when there is light, but let's take for now. If I have a high resistance across here and a very low resistance comparatively, 800 might doesn't sound like it's low, but it's low compared to 2 million, then the output voltage across here, or the voltage across here, is going to be almost an entire 12 volts, leaving 0 across our 8-ohm resistor. So nothing will happen in this hypothetical circuit. Okay, so make sure you understand why a super high R here gives you 0 voltage downstream, so to speak. Okay, now we shine light on it. And when we shine light on it, the resistance of the LDR, okay, drops dramatically, orders of magnitude to 400 ohms. So what is going to be the output voltage across here? All right, what share of the 12 volts is it going to get? There's a lot of ways we can do this. You can figure out the current in the circuit, you can figure out the effective resistance of the circuit, therefore the current, and then do Ohm's law. Nothing wrong with that. There is a shortcut that we learned for series circuits, and that basically means the voltage across any resistor, in this case we want the output, is going to equal a fraction of the EMF, the EMF being our voltage source here. So I'm going to label that epsilon, even though that term might not have been formally introduced yet to you. Okay, so it's a fraction of that. What fraction is it? It's the fraction of the output resistor, the one in question, divided by the effective resistance of that circuit. Okay, so let's make sure we apply that correctly. So we want to know what the output voltage is. So I'm going to change VR to V output. They're the same one. That's going to equal 12 volts. That's our EMF. Okay, what is our output resistance? This is the one we're interested in. That's 800. And what's our effective resistance of the circuit? Well, their circuit is these two resistors. They're in series. So that's 800 plus 400. Okay, so that's 800 over 1200, or 8/12, or 2/3. So it's 2/3 of 12, which is 8 volts. Okay, so we have an output voltage of 8 volts when we turn this light on. So it goes from having 0 volts across it when there is no light to 8 volts. All right, so this analysis here is common for any series circuit. It's not particular to an LDR. The only thing that makes LDR unique is that light changes the resistance. Okay, other examples that are similar to this, all right? And this is not necessarily a sensor, but it really boils down to the same problem. It looks at a voltmeter, okay? So let's look at what happens when we have the resistance of a voltmeter is high, because that's what they're supposed to be. They're supposed to be very high, but not high enough. What the heck does that mean? That sounds kind of arbitrary. So let's say I have a circuit where I have an EMF of 12 volts across here, all right, and I have in that two resistors, a 20 mega ohm, so it's a really high resistor, and another 20 mega ohm resistor, and I want to measure the voltage across here, okay? And my voltmeter has a high resistance, 20 mega ohms, but it's not higher than the resistors themselves. So what's the consequence of that? That's what we mean by not high enough. It's got this resistance has to be significantly greater than the resistors that it's measuring. And that's usually the case we've done in lab, but we want to understand what happens when we have the not so uncommon large resistance you might find in computers, circuit boards, etc. So let's do before. Let's figure out what the voltmeter should read before we actually connect it. Well, I'm not going to go through all the analysis, the derivation of the equations, but let's look at this. We have two of these. We're going to ignore this right now. We're pretending that's not connected. They have the same voltage, so they have to have the same voltage drop across them, and they have to add up to 12 volts. So it doesn't take much to figure out that this has to have a 6-volt drop, another 6-volt drop. So we expect the voltmeter to read 6 volts. Okay, now let's suppose we connect it, and we want to verify that it's 6 volts. Well, we've now created a combination circuit. So we have, this is in series with a parallel branch of the resistor and the voltmeter. So the voltmeter is acting as a resistor. Under normal circumstances, this resistance would add nothing to the circuit. But now it's going to have an effect. So what I want to do is find the effective resistance of this branch. Well, we have two of them in parallel. They're the same value. So we learned a shortcut. So a shortcut is the resistance, effective resistance of these two in parallel is the value of 1 divided by the number in parallel. Since there's 2 in parallel, 20 divided by 2 is 10 mega ohms. So that whole thing becomes 10 mega ohms. Now you could use the 1 over R equation. 1 over R resistance equals 1 over 20 plus 1 over 20, and solve like that. You'll still get 10 mega ohms. So this is in series with this whole thing. So we have 20 plus 10 is 30. Oh, I'm sorry, I need to find that. Let me take that back. So that changes things. This whole branch has half the resistance of this branch, or this resistor. So this resistor is going to get twice the voltage drop, because the voltage drop is going to be I times R. They have the same I's. This has twice the resistance, so twice the voltage drop. Work out the math. This is going to have a 4-volt drop, and this is going to have a 2-volt drop. So the voltmeter will lead 2 volts. Which it's not supposed to do. So that's an important lesson we want you to understand, is voltmeters by design have a very high resistance, ideally infinite, and 20 mega ohms is usually close to infinite, but when you have very high resistances, it's going to give you a false reading. Going back to ammeters, ammeters are supposed to have 0 resistance, or at least less than the wires. So if you were to put a circuit where the resistor, the ammeter's resistance was close to the things you're measuring, it would give you a false reading as well. All right, I'm not going to do the last part, the potentiometer. It's not super important, so we'll leave it at that.